Blocking. So I'm Derek, and this is Will. We will be presenting on behalf of our group. PolarSkin is a process aimed to enhance any high-loft insulation material for its insulating ability.
Sorry, computer.
Yeah. So we will be going through several topics today, and the top arrows would indicate our progress throughout the presentation. So let's talk about the problem that we're facing. In case no one noticed, we are in the middle of the longest and the coldest winter for several years. We all know that keeping us warm is very important. That's why we put on winter jackets. But winter jackets are usually bulky and thick, and making it very hard to maneuver when wearing it. So why can't we have thinner jackets but still stay the same, still stay as warm? And why hasn't anyone thought about using nanotechnology to make these insulation warmer? These are some of the questions that we try to address through PolarSkin. Our mission and our customer requirement is very simple. There are three main points to it. First, develop a treatment that works on any sort of high-loft material. Second, enhance the thickness efficiency of these with this treatment. And finally, develop a process such that it is easily employed into the current industry situation. So to achieve a good insulation, we first have to understand how heat is transferred. I believe all of us know the three modes of heat transfer: conduction, convection, and radiation. Since in a lofty material, the space is mostly occupied by air, conduction is actually negligible due to the low solid volume fraction. The remaining two methods are convection and radiation. These two methods dominate the heat transfer in high-loft materials. Convection is achieved through the movement of fluid, for our example, rising of a hot air. Therefore, a good insulation should impede the movement of such fluid. Radiation is emitted by all matter with temperature higher than absolute zero and transfer in the form of infrared. To retain heat, we would either want to absorb infrared from outer source or reflect them back towards the heat source. So just like how polar bear keeps himself warm, PolarSkin treatment approaches the problem through addressing convection and radiation heat loss. Researchers have proven that microfibers are very effective in creating insulations. In theory, nanoscale materials with a higher surface area would be even better. And using metallic materials, we would also be able to reflect radiation off our body back towards the heat source to retain more heat. The materials with these desirable properties are actually widely available, but we've decided to use silver nanowires. There are several reasons for it. First of all, safety. It is much safer, since we're applying it onto clothing, it is much safer to use silver nanowires versus carbon nanotubes. And silver nanowires are already widely adopted in the clothing industry. For instance, we can get silver nanoparticle socks that prevent odor from forming because of the antibacterial properties, and also the conductive gloves that allows us to use our smartphone while wearing gloves. So it's already widely available and already widely adopted in the clothing industry. So now I'll hand it over to Will.
Hey guys, so we're just gonna talk a little bit how we conduct the experiment and how we design a product. First of all, let's talk about the silver nanowires. The silver nanowires we use in our product has the average radius of 150 nanometers, and it has the average length of 2 micrometers. And they're pre-suspended in isopropyl solution from the supplier. This is an SEM image that proves the property that I just mentioned. Okay, so let's talk a little bit about the process. We create different dilution of the silver nanowires to spur the solution according to the required loading factors. And before the application, we use the base material were mechanically loosened. So we just kind of used our hand and just loosen it up a little. And then the base material is being submerged in the solution to allow dispersion of the silver nanowires throughout the material. And then we heat the sample to evaporate isopropyl, leaving the silver nanowires entangled with the fiber matrix. And finally, we prepare the sample for testing. The two base material that we choose to use were just medical cotton balls and also polyester taken from a winter jacket. We mix the samples according to these loading factors. The loading factors mean we expect these material after treatment will have nanowires with weight 30, 40, or 50% of the material's original weight. And this is an SEM image of the polyester 50% loading sample. As you can see, this is the before image and this is the after image. Before image, we lack of all these nano-silver wires that we have currently, and this confirmed that our experiment works and nano-silver wires were entangled with the polyester. And this is the same thing for the cotton. As you can see again, this is the before picture and this is the after pictures. And once again, it proves that our experiment works and the nanowires are successfully entangled. So let's talk about the testing. How did we test if PolarSkin was legitimate? Of course, we got to test the heat efficiency. So there's 3 types of tests that we did, and we're using the data extracted from the experiments. First one is loading efficiency, and the second one is heat flow across insulation, and the third one is thickness efficiency. So let's talk about them one by one. The loading efficiency relates to how much of the nanowires from the solution stays within a fiber matrix of the sample. We can calculate the loading efficiency by measuring the difference of weight between the expected weight change and the actual weight change. Okay, so the measurement for heat flow across insulation require a little bit more equipment. We have to measure the atmosphere temperature difference across the insulation. And then we use that information to calculate the thermal resistance from the power input. And this is a picture of our setup. As you can see, on the left, there's all the equipment that we used, and then there's the cross section of how our testing was being conducted. Finally, the heat flow test is applied to different thickness to determine the thermal resistance of different thickness and densities.
So after rounds of testing, here are the results. The loading efficiency was found to be relatively low for cotton, but significantly higher for polyester. Since there's no surface functionalization, we expect that the loading efficiency to be low. And previously, SEM images also confirmed that cotton has a lower loading efficiency compared to polyester. Since the loading efficiency for the 30% and 40% loading cottons were very low, we decided to only test the 50% cotton and polyester for more representative data. This is a graph showing the time versus temperature evolution of our samples. We can see that the treated cotton, which is the yellow curve here, and the non-treated cotton, which is the blue curve, reach a different final temperature. The blue curve reached a final temperature of 25.55 degrees, and the treated cotton reached a final temperature of 24.17 degrees. That's a temperature difference of 1.48 degrees, and similar situation to the polyester sample with a final temperature difference of 1.11 degrees.
And I just want to add on a little bit, the more important aspect of this data, it shows it takes a longer amount of time to reach the same temperature for normal cotton and compared to the cotton that's being treated with nanowires. This means it takes a lot more time for the heat to release from your body to the outside environment, and which contain heat to your body.
From the data acquired, we also calculate the thermal resistance of all samples. Here are the results for the main prototypes at a thickness of 2 centimeters. We found that with 50% loading samples, cotton had a 24.45 percentage increase in the thermal resistance. And for the polyester, we have a 17.87% increase. The base cotton and polyester samples were treated with the same volume of isopropanol alcohol and except with no silver as a control test.
Okay, so through multiple tests, we measured the thermal resistance of cotton and polyester samples with different insulation thickness and density. The first plot basically described the thermal resistance with different thickness. We found that for every thickness of insulation, the nanofiber insulation composite always have a higher thermal resistance for both cotton and polyester. And the second plot describes the thermal resistance with different bulk density. The treated cotton display higher thermal resistance relative to its base counterpart across all bulk density. This indicates the treated cotton also gives superior weight efficiency to gain a particular thermal resistance.
So as in, we would be able to achieve the same thermal resistance with a lighter, with less amount of the insulation material.
So in other words, you can just make a thinner jacket as the bulky jackets we have, compared to the bulky jackets we're wearing in winter, and have the same type of insulation we're having right now. So in terms of future steps, there are three major things that we're thinking about. First, we have to improve the nanowire retention. We have to increase the loading efficiency in different materials. Since nanowires are not that cheap to manufacture, this would be an important aspect. This can be done possibly by functionalizing both the substrate or the nanowires. And the second of all, we have to improve the dispersion method. It is potentially possible that we can incorporate spring system, atomizer, to allow for more uniform dispersion of the nanowires. And we'll like to explore how the treatment process will enhance high temperature purpose insulation. Since the radiation component of heat transfer in high temperature is more dominating in high temperatures, we expect that silver nanowires will be fully utilized, both inhibiting convection and greater amount of radiation.
So to conclude our project, I would like to address our objectives one by one. First, thermal resistance. In our previous data and graphs, we show that we have promising result that our treatment actually enhances the insulation ability of these high-loft materials. In terms of thickness efficiency, we also see that there is an enhancement in the thermal resistance at all the thickness that we tested. And in terms of industry incorporation, since most of our clothing today goes through many cycles of chemical treatment that involves submerging the whole garment into chemical solution, this treatment would be actually very easy to be incorporated into the current industry. So in that regards, we have successfully met all our objectives and customer requirements. And thank you for attending our presentation. We will now take questions.
Okay, so seems we have lots of time for questions.
Yes.
After we'll start.
We're 2 minutes early. Yeah, 2 minutes short.
So have you thought about the cost, right? So if you want to get that much
Yes.
cheaper.
Oh, cost is a major problem currently because in the scale that of our experience, we basically purchase a small amount of nano silver wire from Sigma Outreach. So in that sense, the cost is high because the amount that we need to process 1.7 grams of cotton will probably cost us around $15. And this is honestly kind of inefficient in terms of making a whole jacket. But then again, if we think about large-scale implementation, and large-scale nanowire synthesis can also be processed, and that can sufficiently lower the cost to a point that will be largely feasible. But
by how much? Like we have an estimation, like now you have a jacket, right? So if you put half the weight of those cotton by your silver, it's going to increase the material cost by.
it will increase the cost again.
How much?
Again, it's hard to say currently because you have to contact industry to figure out large-scale manufacturing and see how the price is going to change, right? And second of all, there might be more research being conducted before we can figure out the most effective, cost-effective manufacturing way. And third of all, a really important aspect of this product is cost will not be a very, very important aspect of extreme application. Because people that want to use this technology will be people that works in extreme weather, like let's say military in Arctic military actions. Like cost would not be a very main concern, as long as it's not over a scale like 1 million for a jacket, but as long as it's purchasable.
For instance, there are commercialized products that have titanium coatings on the inside to reflect body radiation. Those kind of applications are actually already out there. and this is only a step forward, a step ahead of that. And those jackets are mainly ski jackets that cost about 300 to 400 bucks Canadian for a jacket. We don't expect that our product will be much more expensive than those kind of jackets.
Thank you.
Yes, sir?
So you use this metal nanowire.
Mm-hmm.
The bulk thermal conductivity of the metal is always much higher.
Mm-hmm. Mm-hmm.
So if we look at high-loft materials specifically, most of the spaces are actually occupied by air. So as I explained in the earlier slides, the heat transfer by conduction is actually negligible compared to convection and radiation. That's also pointed out by several research papers that we went through, and the dominant type of heat transfer is done by convection and radiation in high-loft materials. That's why we don't do it with a fabric. We do it with high-loft materials, because that way we will be able to effectively increase the surface area of it.
In your prototype sample, what is the weight percentage of this nanowire?
Right now, we would, as you see, the loading factor is 50%. We were expecting to get that. However, the percentage right now is around 10 to 20% maximum. After treatment.
It's increased by 20%.
Yes.
Have you tried different percentages and measured the enhancement of the thermal?
Yes, we did. We did try different percentages. However, because at lower percentage, the loading efficiency is even lower. As we can see in a slide here, it shows that at 40% loading expected loading factor, we only achieved a 9% or 12% loading efficiency. So that for those samples, we don't really have much nanowires on it to properly justify a testing on.
So my question is, when you add in more and more nanowire to the sample, so at a certain percentage, you will see this nanowire start to join together.
Mm-hmm.
In that case, this bulk thermal conductivity will be more significant.
Right.
So now at a low percentage is okay because they're not connecting. But at a higher percentage, certainly, you are getting more radiation blocking, but you are going to
Increase the conduction of it. Yes, that would be addressed by the dispersion of the nanowires. So depending on how high of a percentage that we go, since we're only testing at the maximum of 50% loading efficiency, we didn't see any of that effect yet. So if we were to go to a higher percentage, let's say 200%, then it start forming a layer of silver on top of it, then definitely yes, conduction would be a problem. But right now we don't see it.
Mm-hmm. And we don't see it being necessary to push to a loading factor that high, and therefore we never conduct more than 50%.
Because as you increase the loading factor, you also increase the weight of your insulator. And in that case, we wouldn't want to decrease our weight efficiency to achieve a higher.
There's also a pretty strong diminishing rate of return in terms of the amount of nano silver we deposit onto the cotton.
Just follow up the question.
Mm-hmm.
The way you choose silver for insulating, a little bit awkward because we know silver is conductive
Mm-hmm.
both thermally and physically. But you mentioned you use the main mechanism for insulation is convention.
Yep.
So my question is, why not use other nanowires?
We had also another major consideration was using carbon nanowires.
Yeah.
But after doing research, and we read a few research papers saying their toxicity really concerned us, and therefore we adopted nano silver wires since there happened application use on other fabric, and we thought that the safety of it will be more suitable for our application.
Have you thought about cellulose fiber?
Sorry,
We
silicon?
thought about cellulose fabric. However, because of the radiation aspect of heat transfer, we also wanted to include that in our product, not just through the impedance of convection, but also reflecting radiation back towards the heat source. So we get the two heat retention instead of one.
Another question is about durability. You put silver in the bottom, you can retain the particle. But how durable is
Well,
As we mentioned, this is an future step for us. We have to investigate on how to better retain these nanowires. Right now, there's no functionalization or surface chemistry to hold them onto it,
right now it's just mechanical entanglement.
tangled within. So we would assume it would have a very low durability if we were to test it right now.
because that's important to know.
Yeah. Therefore, functionalizing it will be the next step of the project.
Okay, I think in the interest of time, we have to stop here. Thank you, speakers.
Thank you very much.